In the past I bought this very interesting Hall sensor unit. It was very cheap and I tried to make all kinds of applications and circuits with the help of that Hall sensor, and especially I was working on circuits where there could be a tiny current flowing here through that Hall sensor unit. That's here. Tiny current, say 1 wire, that goes alongside that Hall sensor, and then I wanted to get a good idea about the current flowing in that 1 wire. I did many experiments in the past days. They were not successful. I can show, say, all the experiments that I did, but anyway, I only want to publish circuits that are usable and tested, etc., etc. And this is a circuit that was usable and tested, and here we have, say, the Hall sensor unit. Here we have the power supply, 12 volt in, 5 volt out. That Hall sensor unit is supplied by 5 volts. That's more or less a standard nowadays, 2021. Anyway, no problems with that. 12 volt in, 5 volt out, and there are 2 electrodes on that unit, and they are here and here, and these 2 electrodes give out a certain voltage, be it positive or negative, when a magnet enters here the Hall sensor. So we get a kind of swap in voltage between these 2 electrodes. But anyway, I made this circuit, and that's very simple. It's a classical Darlington made with a BC547B NPN transistor and a BD139. That BD139 drives the relay. That relay is here. The DC resistance of that relay is 270 ohms. It was made for, say, 12 volts. Could also be 13 volts, 14 volts, etc., etc. But the official naming is 12 volts. Here is the circuit. Looks perhaps somewhat strange, but there is no, in fact it's very simple. Here we have the voltage regulator, voltage in, voltage out. Voltage is 12 volt in and 5 volt out to supply this unit, the Hall sensor unit. It has to be supplied with 5 volts, and amplifier is here. It's a classical Darlington amplifier. I've published this circuit many times on my YouTube channel. I used the BC547B as a first transistor in the Darlington, a BD139 in the second transistor. There is a diode here that kind of protects the circuit for high voltage pulses. It's not strictly necessary, but anyway, I had a few discussions about that on my YouTube channel in the past, but anyway. And what we see here is that when we say use a magnet here and move it into the Hall sensor that's here. You can hear the relay click, so the relay is activated. And the reason why it happens so slowly and delayed is given by this capacitor here. It's a 470 microfarad capacitor, so that makes that this time dependent circuit voltage coming out of the Hall sensor unit and is sent via a resistor here to that capacitor, makes that the whole circuit acts. In a kind of way delayed. So I've now taken out that capacitor, will remove the wire, etc, etc, and let's see what happens when we add, say, the magnetic field to the sensor. And it's now, you can hear it. Very, very sensitive. So the relay is activated, and of course with such a relay you can activate everything. It was not here in this schematic, but of course there are here relay contacts, 1 or 2 or more, etc, etc, via which you can activate a lamp or a motor or whatever. So a good idea, a good schematic to, for instance, to be used in activating an electric motor, etc, etc. And you can say affect the way that an electric motor is activated by using or changing the value of that capacitor. Thanks for watching. That was all. Pen over somewhat. Finally, pin connections. Power supply for the Hall sensor unit. Type number of the Hall sensor unit. This has nothing to do with this video. And here the Darlington that drives the relay. The diode that protects in a certain way the Darlington and the Hall sensor here. And you can set the sensitivity and how it works with the help of this potentiometer. And that's here in the circuit. Here. 500K.